Hi, and welcome to 15.1 Electromagnetic Spectrum. This is the first lesson in Unit 15, Electromagnetic Waves. So we'll keep a basic definition of what an electromagnetic wave is. Let's say you have an electric charge, like maybe it's an electron, and it's moving back and forth. You have a moving electric charge, so that creates a disturbance in the electric field. And in Unit 12, we learned that a moving charge creates a magnetic field. So if it's moving back and forth, you have this disturbance in the magnetic field. And now you have a disturbance in the electromagnetic field. The two are kind of interrelated there. And the energy propagates through that electromagnetic field. Throughout the entire universe, there's only one electromagnetic field, but you could have ripples in that field, waves. And basically, the oscillation can happen slowly or faster, and that will change the frequency of the electromagnetic wave. So in today's lesson, we're going to talk about these waves, their properties, and we'll also look at the electromagnetic spectrum, which is kind of like a list of all the different types of frequencies that you could have in the electromagnetic field. So let's take a look at that really quickly in our reference table. I'll give you a tour of the reference table stuff that you'll need to know, starting with page 1. On page 1, they give you the speed of light in a vacuum, which is 1, 2, 3, 4, 5, 6, 7, 8. So that's 300 million meters every second. So in 1 second, light can travel 300 million meters. That's very fast in a vacuum. Through different mediums like air, like light travels through air, or glass, light could travel through glass or water, that will actually slow down the speed of light. The fastest you could get in the universe is the speed of light in a vacuum. But that's not really the full story. It's any electromagnetic wave. So we typically say visible light. We like the speed of visible light because that's what our eyes are tuned to see. But there's actually a whole lot. Oh, by the way, they use the letter C, right, instead of V. It's just because it's such a special speed that they give it C, the speed of light. So anyway, yeah, it's not just the speed of light. Our eyeballs are tuned into this specific frequency of the electromagnetic spectrum. And this is the whole spectrum, and our eyeballs can only see this much of it, and they have to zoom in over here. This is visible light, and it's not to scale, they say. They just separate up all the different frequencies of the different colors of light here. Let's look at this electromagnetic spectrum diagram that's in your reference table. The top is the wavelengths. So you could see it's in meters. We have a small amount of meters. This is gamma rays. So they are very close to, like even closer, super close together here. And then the spectrum is all about, well, now the wavelength is increasing. And you could have electromagnetic waves that are not 1,000, 10,000 or more meters wide for one wavelength. And that would be radio waves. So you get everything from gamma rays to radio waves in the electromagnetic spectrum. And we could only see a small portion of this. Certain frequencies our eyes are evolved to see. So on the bottom, you also have the frequency. I kind of erased. Let's undo what I did there. Boom, boom. Okay, so for the frequency, you can see when the waves are closer together, that means that if they're all traveling at the same speed, since their waves are closer together, you get more waves per second. The waves go by you more frequently. So by this point in the year, you should, whenever you look at the waves being closer together, you'd be like, oh, that means it's a short wavelength and a high frequency. So yeah, this is a very high frequency. That's 10 to the 21 waves per second. All right, that's a lot of waves every second in gamma rays because they're so close together. Look how tiny the wavelength is. And they're moving so fast in a vacuum, 3 times 10 to the 8 meters per second. And the frequency gets lower. So here the wavelength got higher as you go to the right. Now we can see the frequency is getting lower as you go to the right. So there's less waves per second. But there's still a lot of waves per second because they're moving so fast. You'll still get a lot of waves per second, even though they're so far out. That's a lot of meters apart. All right, but the important thing is that this table is here for you and you don't have to memorize any of these numbers. So in this lesson, we're going to be referring back to this table a lot. All right, so let's see. Number one, radio waves, which are part of the electromagnetic spectrum, are propagated through the interaction of electric and magnetic fields. That's choice B. Number two, electrons oscillating with a frequency of 2 × 10 to the 10 hertz produce electromagnetic waves. These waves would be classified as, and then you get your choices there. We're looking for a frequency that's to the 10th power. That's what we're going to look at over here. So let's see. We're looking at frequency and we're looking for 10 to the 10 power. So we're looking for, maybe it's microwaves or radio waves, something in this little spectrum here. Let's see. Radio waves or microwaves? We're going to go with microwaves. Number three, compared to the wavelength of red light, the wavelength of yellow light is shorter, longer, or the same. So we're looking for red and yellow, back to the spectrum. So where are red and yellow light? You have to look in the visible light spectrum down here. Red light is here. Yellow light is here, and they're asking about the wavelength. And the same thing holds true as you go to the right, the wavelength is getting larger. So as you go to the right here, the wavelength is getting larger. Red has a larger wavelength. Let's see how the question's worded. So we said red light has a larger wavelength. So compared to the wavelength of red light, the wavelength of yellow light is shorter. Number four, an electromagnetic AM band radio wave could have a wavelength of, and then they give you all these different numbers. Remember, the spectrum is given in terms of powers of 10. So let's put these in terms of powers of 10 first to make it easier for ourselves. So this is 5 times 10 to the negative 3 meters. This is 5 times 10 to the 0 meters. This is 5 times 10 to the 2 meters. And this is 5 times 10 to the 6 meters. So we're actually looking for these powers for AM and wavelength. So AM wavelength, let's see. Here's AM radio waves. That wavelength is between here and here. So anywhere between 10 to the 2 and 10 to the 3. It's like just at 1,000. So if it's bigger than 1,000, that's no good. And this is just at 100. So anywhere between 100 and 1,000 is what we're looking for, meters for the wavelength. So that would be choice C, 500 meters, and it was in that 10 to the 2 band, so that's good. Number 5, when X-ray radiation and infrared radiation are traveling in a vacuum, they have the same what? So this is just kind of a property of electromagnetic waves. We mentioned it earlier when we looked at the first page. When traveling in a vacuum, all electromagnetic radiation has the same speed, 3 times 10 to the 8 meters per second. That's the fastest you could possibly go in the universe. It's a very important speed, and it's actually the speed of all electromagnetic radiation, not just visible light, in a vacuum. So we're looking for something that they have the same, something in common. Well, it's going to be the same speed. The frequency and the wavelength are different because they're on different portions of the spectrum. And the smell, I don't think they really smell. So number 6, in each of the following pairs, circle the form of radiation with the longer wavelength. So now we're looking for the longer wavelength between red and blue light. So here's red light, here's blue light. Wavelength increases as you go to the right. So that means red has the longer wavelength. Red. And then microwaves or radio waves, which has the longer wavelength. Well, here are microwaves and here are radio waves. So they kind of overlap with each other, but in general, which one would you say has the longer wavelength? I would say radio waves, because they're on the right. So right, because it increases, increasing. So if they're on the right, that means they have a longer wavelength. Radio waves. Number 7, kind of similar, but it's different. It says, in each of the following pairs, circle the form of radiation with the greater frequency. All right, so now we're looking at frequency, not wavelength, and we're looking for yellow or green light. So here's yellow light, here's green light, and now we're looking at frequency. And what happens to the frequency as you go to the right? It starts high and then it gets lower. So now it's kind of like the opposite. We're looking for, this is decreasing. So the things on the left are going to be higher, which means that green has a higher frequency than yellow does. Yellow has a greater wavelength, but green has a greater frequency. So that's green. And then now again, greater frequency, ultraviolet radiation or violet light. So here's violet light, and that zooms in over here. So violet light is right here, and ultraviolet light is to the left of it. So which one would have a greater frequency? Well, as you go to the right, it's decreasing in frequency. So that means ultraviolet has a greater frequency than violet light does. So ultraviolet has a greater frequency than violet. Let's go back. Here's something we didn't really talk about in this video. See how this is violet? And then what is this? Ultraviolet. And see how this is red? And what's to the right of red? This is infrared. So we've actually seen the prefixes ultra and infra before in this class. In Unit 14, we talked about sound. And ultrasonic means above human hearing. Just like ultraviolet means above human sight. So we have violet, but there's a greater frequency, ultraviolet, that we cannot see, but it's still there. Same with infrasonic and infrared. Infrasonic means the sound waves are below human hearing. We cannot make out those frequencies because it's below the range that we can make out. There's infrared, which is below the visible light spectrum, but it's still electromagnetic radiation. So this is visible light for humans. Our eyeballs can see this narrow band of the electromagnetic spectrum, but there's ultraviolet and then things with a greater frequency than ultraviolet, and then there's infrared, below red, and then there's things, electromagnetic waves with a frequency less than that. So that's kind of interesting. So number 8, kind of similar to previous questions we've done in this class. It says, how long will it take light to travel a distance of 100 meters? And there's actually an assumption that you have to make for this one. So that maybe we should say, how long will it take light to travel in a vacuum? A distance of 100 meters in a vacuum, right? So the distance is 100 meters. We're going to do the guess method. And there's a piece of hidden information here. The velocity is equal to c in this case we'll use, and it's 3 times 10 to the 8 meters per second. That's on the front of your reference table. I showed you before. Right here, 3 times 10 to the 8 meters per second. Now, what's the unknown? It says, how long will it take, which means, like, what's the time? How long is this going to take? All right, so we'll do our good old formula. V is equal to D over T. One of our last units, but we're still using this very great formula, the first one we learned. And again, be careful when you're solving for the variable and it's in the denominator like this. It's easy to divide by the wrong thing. So I recommend cross multiplying, taking your time. And now hopefully you can see you actually have to do 100 divided by 3 times 10 to the 8. So that's what goes in the denominator there in your calculator. And when you do the division, you get 3.3 times 10 to the negative 7. What are the units for time? Seconds. Now, this might seem like a super small number. Maybe a red flag's popping up in your head. Maybe I did something wrong in the calculator. Is this really right? Well, yeah, if you think about it, 100 meters is about the length of a football field, and we're talking about light traveling. So it's going to take light, which is very, very fast, a very, very short amount of time to travel only 100 meters. Number 9, similar. It says the distance from moon to Earth is 3.9 times 10 to the 8 meters. So there's your distance. So it says, what is the time required for a light ray to travel from the moon to Earth? Well, if the light's traveling from the moon to Earth, it's traveling through a vacuum. So the speed of that light is equal to 3 times 10 to the 8 meters per second. And they're looking for the time. So you could just do V is equal to D over T, substitute in, solve by cross-multiplying, and then dividing. And you should get a time of about 1.3 seconds. So it takes 1.3 seconds for the light to travel from the moon to Earth. Now remember, obviously the moon isn't creating any light, it's reflecting the light from the sun. So the light from the sun goes to the moon, then it reflects to the Earth. But as the light is being reflected from the moon to Earth, it takes 1.3 seconds. So if the moon were going to like explode or something like that, it would actually take 1.3 seconds for us to even realize it. So the moon would have exploded. But if we look up at the sky and for 1.3 seconds, it still looks like the moon is there because it takes light time to travel. It's not instantaneous, but it's very fast. Number 10. Orange light has a frequency of 5 times 10 to the hertz, 10 to the 14 hertz in a vacuum, so that's the frequency. They're talking about light in a vacuum, so we know the speed. And they're asking, what is the wavelength of this light? Now, you might be tempted to try to use your electromagnetic spectrum, the diagram in your reference table, but you won't be able to get a precise answer. If we take a look, sure, orange light is right here, and they tell you it's any frequency between this and this. So yeah, 5 times 10 to the 14 hertz, that's in between those two values. That's orange light. But you can't extrapolate this and like try to look up and see what is the value of the wavelength. This is a huge difference in the numbers. You can't just like assume the number. A better way to do that would be to use our wave equation. So the wave speed equation on page 5 is still holding true, but instead of V is equal to F lambda, we could use C is equal to F lambda when we're talking about speed of light or any electromagnetic wave in a vacuum. So we could use, if we wanted to be fancy, C is equal to F lambda, or V, doesn't really matter. 3 times 10 to the 8, 5 times 10 to the 14 hertz, solve for the wavelength, and you get 6 times 10 to the negative 7 meters. So that's a more precise answer than trying to look at the diagram, the spectrum in your reference table. So that's what the actual wavelength is of that light, of that electromagnetic radiation. So number 11 says, what is the frequency of a light wave with a wavelength of 6 times 10 to the negative 7 meters traveling through space? We just solved for that. So it should be the same thing, right? So the wavelength, and if it's traveling through space, light traveling through space, that's light in a vacuum, so we know the speed. And now they're asking for the frequency, but this should look pretty familiar. We're going to do the wave speed equation, plug in what we know, and when you do the division, you get a frequency of 5 times 10 to the 14 hertz. So this is just a little practice with the wave speed equation, again, seeing how it works. All right, so number 12 says, which color of light has a wavelength of 5 times 10 to the negative 7 meters in air? Which color of light? A wavelength. So let's try to use our table. So here they are, the colors of light, but they're giving us the wavelength. And these numbers down here, see how they're all 10 to the 14 and they're below the stuff? See how this is 10 to the 14? These numbers are the frequency, and they should really make it more obvious. These are all the frequencies. They don't tell you the wavelengths. It'd be nice if they had numbers up above over here telling you the wavelengths of these things. But I guess it would make the table a little bit more cluttered. And so they're like, well, you could figure out what the wavelength is if you really wanted to. Well, the problem is they tell you the wavelength now. So we're going to have to figure out what is the frequency, and then we'll look over here and we'll see where does that frequency fall and what color of light is that. So first we have to figure out what's the frequency. So they're telling you the wavelength. Now it says in air, we'll learn later when we talk about index of refraction. When it's in air, it's very close to being in a vacuum. The air is only going to slow down the light a little bit. It does slow it down, but it's still, you could round it basically, and it's still the same 3 times 10 to the 8 meters per second. When light goes through glass or water or something that's more optically dense, it will slow down and you cannot use that number again. But for now, we'll definitely still use that number because air is pretty much the same as a vacuum when you're talking about the speed of light. It only slows down the speed of light by a little bit, and when you round it, it's the same anyway. And now we're looking for the frequency so that we could figure out what the color is by using our table. So we could do C is equal to F lambda, plug in, and when you solve, you get a frequency of 6 times 10 to the 14 hertz. So now we have a number that we can use to look at our reference table. 6.0 times 10 to the 14 hertz. So what color of light is that? Well, it's greater than 3.84. It's greater than 4.82. It's greater than 5.03. It's greater than 5.20. Is 6.0 greater than 6.1? No. So it has to be in between here. Oh, so that means that it's green light. 6 times 10 to the 14 is about here in the spectrum. Okay, so green light. And that's the basic idea for the properties of light and the electromagnetic spectrum. What's really going to be fun is when we do, well, reflection, but also refraction. And like I've been alluding to, what happens when it goes through a medium that's not a vacuum and the light slows down? Very interesting stuff. All right, have a great day.